So, in this video, we're going to introduce vectors. If you are using the Larson Precalculus book, this would be section 6.3. In a Larson Calculus book, this would be section 11.1. And I want to tell you what a vector is, but really I don't know that I could do it better than this guy. So I'm going to go ahead and let him take it from here.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Check out my new weapon. Piranha gun! Oh yes! Fires live piranhas. Ever seen one before? No, you haven't. I invented it. Do you want a demonstration? Oh! Ah! Gosh, it's so difficult sometimes to get the piranha back inside.
Okay, I think he got a little carried away there with the piranhas, but he did mention a couple ideas that we do want to focus on. So he mentioned two words, direction and magnitude. And suppose you had an object, a moving object, like perhaps from your piranha gun, and you wanted to model, like tell someone how to maybe locate a moving object with that piranha gun. So you need to describe two important characteristics, such as the direction of the moving object and the magnitude. Now, direction, well, you've heard bearings before. We might give bearings for an object, or we might have other ways to describe the direction. Magnitude, in a word problem, that might be something like speed or distance traveled. So a vector is able to capture both of these characteristics at one time. A vector might be expressed in this form, so this would be called component form, 3, 4. It kind of looks like a point, but you'll notice I have these pointy brackets here. Some books and some programs will even use just the regular parentheses like we would use for a point. And so if this were an ordered pair, 3, 4, then that represents an object going from a point, say the origin, 0, 0, to the point 3, 4. So a total change here horizontally of 3 and a total vertical change of positive 4. So those two units together, that is telling us a direction, right? 3 up 4, and a total magnitude as well, which we'll discuss. If an object were to move from 0, 0 to the point 3, 4, then you might remember from previous work this semester, that's a Pythagorean triple, so the magnitude would be the distance traveled, so 5 total units because of that triple, and we'll look back at that again. Another term we will use is scalar. Now, scalar does not denote a vector. A scalar just describes a constant term. So in a word problem, that might be something as temperature. It's not moving and non-changing. Something like temperature would represent. Now I want to give you an idea of how vectors work. So much of this lesson will be vocabulary based since it's the introduction, but this website is a neat website to kind of give you an idea of how vectors work. It also is a good one to replace Cookie Crush. So if I click OK to start, you see that we have this ball, and it's going to crash into some of those rectangles, and so they may disappear. I'm going to send this link to you all, and I want you to go through this, and it's actually a game, but you could think of the vector, so when the ball is released, it's going to kill some of the squares. So cancel out some of the squares. Now this arrow that you notice, and I can move this right or left to catch the arrow. This arrow is indicating the direction by the arrow and the speed. So the length of the arrow denotes the speed of the arrow. And if you play this game for a while, and you can actually see the arrows coming out of my part as well, the vectors. If you play this long enough, then they change the speed, and as the speed increases, then you'll notice the length of that vector increases. So here, what the vector is doing is it's indicating the direction and the speed, so that so it's indicating the speed of the direction and the speed of the little ball as it moves around. I'll actually send you this link so that you can play this game as well. The reason I like showing you this is to give us an idea to understand those two descriptions that we were talking about earlier, magnitude and direction. So basics of vectors. I want you to consider a few questions. How do you find the magnitude of a given vector? Sometimes you'll interpret that as speed, but often we'll describe that as a distance. And so keep in mind it would depend on the scenario. Another question I have here that you might be thinking, when are two vectors equivalent? And then another one, why are we studying these in trig? I thought that these were a physics topic. You would encounter these in physics. However, a lot of the same concepts, so because we're learning about trigonometry and trig functions and angles, then we want to build those basic skills. And so I'm going to give you some of the formulas that you might use in a physics class, and we're going to apply some of the trigonometry we have learned. If you click here, I've included a drone. So this is drone footage of some dogs playing at a park, and I've actually taken a clip from that. And in that footage, this man, the owner of one of the dogs, he throws a toy. The toy is landed somewhere over here. And the dog started right beside him. Now in this image I've taken, you can see that he's already running right towards the toy. And in real life, when would the vector of the toy match the vector of the dog? Well, that would only be the case if the two vectors had the exact same direction. He has to go exactly to the toy, and they also need to have the same magnitude. So in this case, I'm using it as distance. And so that blue vector is offset a bit, but these vectors, in order to be equivalent vectors, they must have the same magnitude and same direction. You'll notice I have parallel vectors here. Vectors can move anywhere around on the screen and they can still be equivalent. But in order for two vectors to be equivalent, so we don't care where the position is necessarily, we just care that they have the same direction, parallel, and that they are the exact same length, and that's what we refer to as the magnitude. So again, vectors, I could slide a vector around and it still could be the same vector. That position of where the initial point is does not necessarily matter. What's important though is that the initial position and the terminal position have the same relationship. So their distance remains the same and the direction indicated remains the same. So magnitude, what is magnitude? All we're doing here is finding the length of the vector. And from Pythagorean theorem, if you have a vector, and here I've indicated the horizontal position and the vertical position, then this would be the hypotenuse, the length of the hypotenuse, and it would be the square root of, so because a squared plus b squared is equal to c squared, then you'll notice I have the horizontal part squared plus the vertical part squared, and you'll take the square root of that to find the hypotenuse. Now, often you might see absolute value bars around a vector. So here you'll notice I don't have a little hat above this, but the letter is bold. So this is an example that I just wanted, I'm going to change some of the notation frequently so that you're familiar with this. We use different, just like with the square brackets versus the parentheses, you might see a single absolute value or you might see double absolute values, which our textbook will use, and both indicate magnitude. Just remember, magnitude is the length of the hypotenuse for that triangle that you build with the horizontal and vertical change, and so therefore it's just that distance between the initial and terminal point. The length in three-dimensional space, if you had a vector it's locating a position. So if it started at 0, 0, 0, this would be the length of that three-dimensional vector. In component form, so if you have the absolute value of a vector, the magnitude of a vector, then in trig we are familiar with the concept. So here you have this image that's in the first quadrant. Your vector, the blue vector, I'm denoting, or I've mentioned the horizontal component and the vertical component. This picture has indicated both of those. And if you were to think about cosine of theta, well, cosine of theta would be adjacent, so the horizontal component over the length of the hypotenuse, which in this case would be the length of the vector. And so because the horizontal component over that length of the vector, if I solve for the horizontal component, then I get that the horizontal change will be absolute value of the vector times cosine of theta, and the vertical change would be the absolute value times sine of theta, because sine of theta is opposite, so vertical, over the length of the vector, and solving for the vertical change, then that gives us the magnitude of v times sine of theta. So what I have here says that any vector can be represented in this form. So again, this is component form. Your horizontal change would be given by this, and your vertical change would be given by this. Now, earlier I talked to you about just using constants for each of these components. That would be terrific if we knew the actual horizontal change. If that's not given, and I do know the magnitude and the direction given by an angle, I can find that, then this will be an easier way for you to represent that vector. And so depending on the information given, then you might need to use one or the other of these. Now a unit vector, you'll notice for a unit vector, instead of a bold letter or instead of a little arrow, this has a little hat. So unit vectors are 1 unit long. If an object were to move 1 unit along the x-axis, then we would denote it with in the component form with brackets 1, 0, so the ordered pair 1, 0. Kind of, you might be thinking about the point 1, 0. If the object were to move 1 unit along the y-axis, then that would be this ordered pair 0, 1, and in mathematics we usually use a j to represent that vector. And here on this image you can see I and j. Now if you combine 3 i's and you combine 4 j's, then the vector 3, 4 represents the exact same vector in component form as this linear combination using the unit vectors. So 3i plus 4j, those are the same. You should be pretty fluent with these. You might be given one or the other and just know that we use those different, they're the same thing, but we might just express those in the different forms. If you were to extend this into 3D, we often use I to still represent that change along the x-axis, but now we would have to give that in 3 dimensions, so 1, 0, 0. J would be 0, 1, 0, and we introduce K along the z-axis 0, 0, 1. Depending on your textbook, this may turn, so we might rotate those 3 axes and they might face a different direction, but K is often used as the change along the z-axis. Now here's an example. We are instructed to represent each of the vectors u and v in terms of their magnitude and direction. So here, I know that the vector u is 4 units long, and this, you could maybe think of the setup of the problem. I know that 35 degrees is between the positive x-axis and that vector u. Notice that u and v are both in standard position here, so vectors can slide all around the screen, but both of these vectors are starting at the point 0, 0. So given this information, we know the magnitude of u is 4, and this direction indicated by the 35 degrees, I can substitute into that form I had earlier. Similarly with v, so that we have u is equal to the magnitude of u times cosine of that angle times I plus 4 sine of that angle times j. So 4 cosine of 35 represents the horizontal change, 4 sine of 35 represents the vertical change. Similarly with 7, you'll notice that because that was 15 degrees between the positive x-axis and the vector v, we used a negative 15. for my angle. And similarly, here's my horizontal component and my vertical component. Unit vectors are often used in applications because occasionally we don't want the value of the magnitude of the vector to interfere in a calculation. So what I've said here, suppose we need a unit vector which represented the same direction as each flight. So when we only want to use the direction but not the magnitude of a vector, then sometimes you might hear standardize it or normalize it. And so what we do in this case, so in such a case, the unit vector would be given by this ratio. And all we're doing here is if you want a vector that just has magnitude of 1, then you simply take that vector and you divide by its magnitude. So for the two vectors we were just focusing on, the magnitude of u is 4. U over 4 would give you this vector in component form. And if you take the magnitude of this, you'd have the square root of cosine of 35 squared plus sine of 35 squared, which is 1. And so you'll notice the magnitude of this will just be 1. Again, the magnitude here was 7 for b, so b over 7 would identify the unit vector. So I'm mentioning this is how you find the unit vector for any given vector. The resultant vector, so as indicated here, a and b would be vectors denoted by bold letters in this case, and the sum, so we call this the resultant vector. The resultant vector would be this green vector, and it's the diagonal in that parallelogram. So if you want a plus b, if you were to walk along vector a and then walk along vector b, so that is the sum a plus b, then the resultant vector is the shortcut between the beginning of a and the end of b. You'll notice you can reverse this order, but here, so b, first walking along b and then along a, so they're actually the same, but the picture you would identify is different. So b, a, the resultant vector starts at the beginning of that and ends at the end. Here I have written that the horizontal component of the resultant vector is the sum of the horizontal changes. The vertical is simply the sum of the vertical changes. Another result of this parallelogram, this is known as the triangle inequality, and I wanted to include this here. We use this quite frequently in mathematics. To give you another idea, I just want to talk about this meme that came out this week, and it actually used an example of the triangle inequality. So the sum of the resultant vector is, the magnitude of that is less than or equal to the sum of those, and hopefully you appreciate that joke. In this next example, so determine the resultant vector. So find the resultant vector, u plus v, the vector that represents the sum of those, and then find the magnitude of this vector. So to begin, we find simply, so you'll recall from earlier that u, the horizontal component, was 4 cosine of 35, and for v, the horizontal component was 7 cosine of negative 35. You'll notice for the resultant vector, the horizontal component is simply the sum of those two horizontal components, and the vertical component is simply the sum of the two vertical components from earlier. We were asked to find the magnitude of this vector. To find the magnitude, we need to take the magnitude of that new vector we found. So that will simply be the square root of the horizontal component squared plus the vertical component squared. And this would be one of those things I would have you expand. If we were at school and I were up on the board, I'd give you a couple minutes, so you might want to pause the video. And what I want you to do is expand this part inside the parentheses. When you do that, I'd ask you to simplify as well. Now I'm going to go ahead before I show you that and go through a little bit of this. Because this is a binomial squared, you have 4 cosine of 35 plus 7 cosine. So two things inside the parentheses squared. You'll have this term squared, so 16 cosine squared of 35. And over here, you'll notice you'll get a 16 sine squared of 35. The next term from this set of parentheses would be plus, you'd have 2 times 4 times 7, so that would be 56, and you'd have a cosine of 35 and then times cosine of negative 35. Over here you'll have a 56 and the product of sines. Your last term from this would be 49 cosine squared, 49 sine squared. Now putting together the cosine squareds and the sine squareds of the same angle, since that's 1, you should have an expression that looks something like this. So from 16 cosine of 35 and 16 sine of 35, that will be 16 times 1, 49 times 1 from the sum of the last two terms, 56, these were from the first binomial, and this was the product that came from that second, and I factored out the 56 here. Now if you'll look at that, because this was given to us in terms of cosine and sine, we can actually simplify this part right here. You might pause the video and think about that. I see a cosine, cosine, sine, sine, and it's a plus. So that makes me think of the difference angle for cosine. So 35 minus negative 15. So that is actually cosine of 50 degrees. I use these constants that I had, and then I could throw that into a calculator, or if I'm asking you to do this without a calculator, then you could simply stop here. This would be your magnitude. When you are working with vectors, there are three types of multiplication. So I'm going to begin by talking about scalar multiplication. If you'll recall, a scalar is simply a constant. So when you are given a vector, as vector u here, is denoted, described by this sum, and a scalar c, then the scalar product simply, so if you had 2 times a scalar, you simply distribute that scalar among the components. And a scalar, that's really all that comes down to. A scalar will affect the magnitude of a vector. So if you have a positive constant, then that's going to double, like if c were equal to 2, that would double the magnitude of the vector. If the scalar was between 0 and 1, then it will shorten the magnitude of the vector. And if the if the scalar is negative, then what that will do is reverse the direction. So if you had a vector that was going one direction, and then you multiplied by negative 1, it's going to go in the exact opposite direction but have the same magnitude. And so keeping this in mind, scalar multiplication will affect the magnitude of the vector, and it could affect the direction by sending it in the opposite direction. Dot products are a different type of multiplication, and the symbol matters. So if you are given 2 vectors, the dot product is a product that is an operation that is done between 2 vectors, and it's simply as defined here. So the dot product of 2 vectors, what you'll do is take the product of the horizontal components, add that to the product of the vertical components. This actually is extended for 3 dimensions. When you worked with vectors, when you worked with matrices before, and you were multiplying matrices, then each element in the matrix was the dot product of the row and the column that element lied in. And so dot product you actually have used when you work with matrices. Matrices are a collection of vectors. So another property that I wanted to point out, any vector, if you take its dot product with itself, then you'll notice, so for u here, I'd have the first component squared plus the second, and this is the magnitude squared, so it's simply missing the square root. So actually, any vector, when you take the dot product of itself, so u dot u is equal to the magnitude squared, and that's a property that you might notice it'll come up occasionally. So we're going to work an example using the 2 vectors we were given before. The dot product will simply be the product. You'll notice that it is a scalar, by the way. So often this is called the scalar product. I didn't want you to confuse that with scalar multiplication, but the scalar product is what we describe the dot product, because the result will just be a number, a constant. No i's or j's are left in this answer. So to find the dot product, you just take the product of the horizontal component, so 28 cosine cosine, and you'll add that to the product of the vertical, so 28 sine sine. You'll notice again I could factor out a 28, and again I have cosine of 35 minus negative 15 from the difference formula. And so the dot product would simply be 28 cosine of 50 degrees. There is a third type of multiplication for vectors, and we call this type the cross product, or sometimes it is called the vector product, because only in this case will you take two vectors and the result will be a vector. I do want to mention this only works for 3D vectors. You could use this for 2D and you would just leave the third component as 0. So for three-dimensional vectors, two three-dimensional vectors, v and u as given, then the vector product is this long, complicated form. Now if we were in class, I would actually show you the link between these, but it's a little, so it takes a few lines and you could do it yourself. If you remember how to take the determinant of a 3x3, then you could actually represent this entire line in this nice form. So the cross product of u and v, so u cross v, is equal to, this doesn't, so here this first row, they're kind of just placeholders. So I'm using I, j, k, the unit vectors, and then the first, or the second row, this would be filled with numbers if you actually had the components for u. So the second row would be the components for u, the third row would be the components for v. Order does matter for these, and so if it's u cross v, you need to keep that specific order. But the determinant of this 3x3, so that's why I've used those absolute value bars, is this expression, and that will give you the cross product of two vectors. That actually has some neat applications, and it's used pretty frequently in, say, a Cal 3 class. So that's the cross product. Recall that we had the dot product before, I apologize, and I'm going to tell you how to get this formula, and we're going to describe how to get where this formula comes from. So if you'll recall earlier, I gave you u and v, and you already found the dot product, given here, 28 cosine of 50. And I want you to recall the picture. Now that 50 degrees happens to be the angle between those two vectors when they are drawn in standard form. So actually, if you'll notice, if you take arc cosine of both sides, then 50 degrees is equal to this expression. Now that 28, how does that relate to the original vectors? Well, 28 happens to be the magnitude of u times the magnitude of v. So I hope that this was making sense. This is the intuition for this slide. The angle between two vectors, this is a formula that you would need to know. So two vectors u and v, the smallest angle between the two vectors is given by arc cosine of the dot product divided by the magnitude of both of those. You'll notice that because arc cosine is defined on the interval from 0 to 180 degrees, if this is equal to, if arc cosine of a value is equal to 0 degrees, then the vectors are going in the same direction, so they're parallel. If this were equal to 180 degrees, the vectors are going in opposite directions. For theta equals 0, then that means that the dot product would be equal to 0. So if you think about this, what's the only time arc cosine would be equal to 0? Well, that would be if this expression were equal to 0. The denominator could never be 0 because we can't divide by 0, but the dot product, that implies that the dot product would equal 0. So the word we use for that is orthogonal, and it means that the vectors, if you were to draw them both in standard position, then there are 90 degrees between the vectors. So that expression that we have here, if you were to take cosine of both sides and multiply by this product, this is called the alternative form for the dot product. So it's really the exact same thing as what we got from the dot product before, or from the last slide. I actually want you to work this in your homework to really understand where that comes from, because you could derive that using law of cosines, which is directly related to what we've been working recently. This chart, it may be a little blurry, this is taken out of your textbook, and I love this chart because it helps you understand how the dot product tells you, it informs you about the angle between two vectors. So if the dot product is negative, if your dot product is, your cosine value here is -1, then, so if the dot product is equal to -1 times the product of the magnitudes, then you know the direction the vectors are going in opposite directions. If the dot product were less than 0, then you have an obtuse angle because your cosine value must be in the second quadrant. If the dot product is equal to 0, you have 90 degrees, so pi over 2. If the dot product is greater than 0, then you must be in quadrant 1 because cosine would be positive in quadrant 1. And then if your cosine value is equal to 1, so if the dot product is equal to exactly the product of the magnitudes, that tells you that the vectors are going in the exact same direction. So an important concept I've said a couple times, but just to make sure that it hit home, this is the orthogonal property. Two non-zero vectors are orthogonal if and only if their dot product is equal to 0. If and only if you're not familiar with proof statements, these statements are, so vice versa. So I can tell you, if I tell you two vectors are orthogonal, that implies that their dot product is equal to 0. If I tell you the dot product equals 0, that implies that they are orthogonal. So this is an if and only if statement, which makes that quite strong. You can think of these as the same, basically the same ideas. So here, I want to introduce the projection. I'm not doing an example here, and I realize that we may need to do a little bit more work in this area. However, I wanted to go ahead and introduce this. So the projection of a vector onto another vector. The projection of u onto v is denoted here. And you might think of this was an image, I have the link where I got this from. You might think of a projection as a shadow. That's an excellent way to think about it. I sometimes talk about holding a flashlight here above you, and if you were to shine that down on you, this yellow vector right here denotes the projection of v. The projection of u onto v. I'm sorry. When I was reading that, the big letter is what you read first, so the projection of u onto v. And that is correct. So the projection of u onto v, the blue vector, would be this yellow vector here. And I want to talk about that formula in just a minute. The projection is parallel to v. Sometimes you might hear this called the rejection. The rejection would be this w, and it is orthogonal to v. So what you notice from this picture is u is the resultant vector of the projection and the rejection vector. So u is the sum of the projection and then along w, the rejection. So sometimes that is called the vector component of u along v. The rejection is called the vector component of u orthogonal to v. Alright, I want to go ahead and talk through this formula now. So here, projection of u onto v is equal to the dot product over the magnitude squared times v. Now a couple things I want you to notice. Do you remember earlier when I talked about finding a unit vector for a vector? I hope so. So v, the blue vector, is much longer in this picture. The magnitude is greater than the yellow vector, the projection. I want the projection vector to be parallel to v, but I don't want the magnitude to influence it. The shadow, it wouldn't matter. The shadow would depend on the size of u. And so, how do you find the unit vector? Well, you take a vector and you divide by its magnitude. So I know I have magnitude squared here, but if you were just to think about v over its magnitude right there, that is finding the unit vector for v. That's where one of these is coming from. The other one, so you have u dot v divided by another magnitude, what that's doing is that's your scalar. And it has to do with the fact that here we want u times v, so remember that that would be your angle and the change of these. So I'm actually going to give you an assignment where I want you to work with this and see if, based on my scaffolding, you can understand where this formula comes from a little bit better. But that u dot v over the magnitude of v is a scalar, and what that's doing is just sizing the projection. So first you find the unit vector, which might be a little baby vector over here, and then u multiplying by u dot v over the magnitude of v is what gives this link that becomes perfectly the shadow. So the projection of u onto v, this is a formula that you will use, and really for right now, it might just be worth writing that down on a note card, and we will come back to it later.